vast majority of relays which are installed on the power system and with which we are familiar are electromechanical relays. The incoming measured signal is fed into a magnetic circuit, which produces mechanical action to operate contacts. These electromechanical relays have proved to be extremely reliable over the years, and in many cases have become quite sophisticated, as those of you who are involved in test and calibration are most certainly aware of. However, on more recent installations, you may find static relaying employed. This may be in the form of solid-state relays or microprocessor relays. In this videotape, we'll look at solid-state analog-type relays first. This type of relay has been around for many years, but most power companies have continued to stick with electromechanical relays because of their familiarity and high level of reliability. However, the static relay does offer certain advantages. It is much smaller and lighter. It consumes far less power in operation. It presents a much lower burden to the CTs and VTs. Its circuitry can be arranged to provide similar and even superior characteristics to equivalent electromechanical relays. The relay reset value can be adjusted more precisely due to the lack of mechanical inertia and overshoot. It has the ability to withstand overcurrent and overvoltages for longer periods of time. As with all such things, there are some disadvantages. Ambient temperature must be kept within specified limits. Therefore, care must be taken with location of the relays. Voltage spikes can damage the relay. It's subject to interference and misoperation from power system transients. Static discharge can damage the relay components during maintenance if the technician and equipment are not properly grounded. Solid-state relays contain a great number of components and consequently a higher failure rate, especially in the first 6 months. In the electromechanical relay, the tripping circuit is energized by closure of contacts, which in turn respond to a magnetic coil. In the static relay, the same result is achieved by some form of gate, such as a transistor. When the signal current achieves a preset level, it effectively opens the gate and current flows through the transistor to activate the tripping circuit. In practice, further amplification and auxiliary relays would be required. Let me make an important point. We are assuming here that you already have a knowledge of electronics and electronic circuits. Even so, I believe a brief summary of solid-state components will be useful at this stage. Diodes and transistors are made of semiconductor material, typically silicon, and this is often treated with other materials such as aluminum and antimony in order to produce the desired characteristics. In the diode, two dissimilar semiconductors, P-type and N-type, are joined to make a PN junction. This can be thought of as positive and negative. The diode allows current to flow from the P to the N side with little impedance, but provides high resistance to flow in the opposite direction. This is why the diode is widely used for rectifying AC to DC. However, if the reverse voltage is high enough, current will flow in the reverse direction. The breakdown voltage is designed into the diode and may be anywhere from, say, 100 to 1,000 volts. Once this barrier is exceeded, the reverse current may rise to a very high value. This is often called avalanche current, and it will quickly destroy the diode unless its amplitude is restricted by some form of series resistance. The Zener diode uses this breakdown characteristic as a voltage measuring device. It is specially made to withstand high current flow. Even so, a series resistor is always added when the Zener diode is used for voltage regulation or circuit protection. You'll often see it connected into a circuit apparently the wrong way round. In fact, the Zener diode symbol shows the positive indication also the wrong way around, but this is correct. We want the device to become conducting when the determined voltage level is exceeded. A special type of diode is the LED, light-emitting diode. When current flows through the diode, light is emitted from the junction. The most common application for LEDs is as indicating lights for electronic circuits, as they respond to very low voltage and current. Another application is to use the LED as part of the protection circuit. When the diode is energized, the phototransistor turns on the output circuit to initiate action. This device is known as an optocoupler. The main advantage is that the input and output circuits are electrically isolated from each other. This keeps voltage spikes and other interference out of the output circuit, which may be, say, a logic circuit. Now let's take a look at transistors. Depending upon the arrangement, it can be connected to provide high impedance to the incoming signal and a low impedance output, or vice versa. The transistor resembles two diodes connected back to back. One type sandwiches the N-type semiconductor material between two layers of P-type material. This is known as the PNP transistor, and it is shown diagrammatically like this. Remember, there is little resistance to current flow between P and N, so the voltage difference can be quite small. The PN junction is known as the emitter. By contrast, a higher voltage difference is needed to cross the NP junction, which is known as the collector. In another arrangement, the P-type material forms the center or base, and this is sandwiched between two N regions. Here is the symbol. By regulating the signal applied to the base, the transistor can be made conductive or non-conductive. Moreover, current or voltage amplification can be achieved. Here is a simple example of the transistor as a switching device. The resistance here represents the operating load, perhaps a trip coil. Application of a very low current, say 0.4 milliamps, to the base of the transistor will produce a base voltage drop of perhaps 1 volt. This will allow current flow through the load of about 20 milliamps, that is, a gain of 50 to 1. The voltage drop across the transistor is extremely small, and essentially all of the power in the circuit is consumed by the resistor. With a resistance of, say, 1,000 ohms, the voltage across the circuit equals 1,000 times 20 milliamps equals 20 volts. The power used by the load is equal to 20 volts times 20 milliamps equals 400 milliwatts. Compare this with the input power to the base, which is 1 volt times 0.4 milliamps equals 0.4 milliwatts. The power amplification ratio is 1,000 to 1. Depending on specific requirements, transistors are connected in a variety of different ways in order to provide amplifier circuits. One very common arrangement is the differential amplifier shown here. This circuit can be used to amplify either AC or DC voltage. The total current flow is determined by this resistance, which is common to both transistors. The two transistors and associated resistances equally share the load, so there is no voltage difference at these output terminals. Let's see what happens when we apply a signal across the input terminals. Let's assume that the number 1 terminal becomes positive in relation to number 2 terminal. Consequently, the current flow decreases through transistor number 1 and increases through transistor number 2, so as to keep the total load current constant. There will now be a difference in voltage across the output terminals, and this is amplified depending upon the gain of the transistors. The advantage of this arrangement is that it automatically compensates for temperature variations. Any change in one transistor due to temperature will be offset by a similar change in the other. The gain of transistors can be considerably affected by temperature changes. As temperature rises, the resistance decreases. So increasing current flow produces just the opposite effect to that of a resistor. Several other arrangements can be used for temperature compensation. Transistorized circuits are so common that a variety of basic circuits for switching and amplification can be obtained already assembled in the form of integrated circuits known as ICs. The integrated circuits, or chips, contain the necessary resistors, capacitors, transistors, diodes, and circuitry, all in miniaturized form. A table of standard symbols for integrated circuits is included in your workbook. A typical example is the operational amplifier, shown by this triangular symbol. This exceedingly small component incorporates a differential amplifier coupled to a push-pull output. The operational amplifier can be connected in many different ways in order to meet different circuit requirements, such as voltage amplification and inversion of polarity, summation of input voltage or currents, subtraction of the input signals, that is, differential. The different connection arrangements for these circuits are included in your workbook, so as to give you ample time for study. Another very commonly used integrated circuit is the thyristor, also known as the silicon-controlled rectifier, or SCR. This is a little different from the switching device that we looked at earlier. The thyristor can be triggered by a single pulse input to the gate. Once the pulse is removed, the circuit remains switched on until it is deliberately interrupted by removing power, for example. A special type of transistor, rather a family of transistors, is known as the FET, that is, field effect transistor. Amplification is accomplished by establishing a current flow through a channel. The resistance of the channel is varied by adjusting the electric potential applied between gate and source. This, in turn, controls the magnitude of current flow. The FET provides a very high impedance to the input, so it is very useful for switching low-level signals. Another type of FET frequently used in solid-state relay circuits is known as the metal oxide semiconductor FET, called MOSFET for short. This diagram shows a P-type coupled to an N-type to produce an inverter circuit, as commonly employed in relay logic. If the input signal is 0, the output will be a positive value called 1. Conversely, when the input is a positive value, again called 1, the output will be 0. We'll be talking more about this in the next segment. Once again, let me remind you that we are not attempting here to teach you electronics, but rather to draw attention to the types of components which will be seen later as we study solid-state relay circuits. If you need to review your basic electronics and recollect how these devices work, now is the time to do it. But for now, let's take a break, and then we'll come back and start looking at static relay circuits. Please turn off the tape and go through this material in your workbook. Most protection relays, whether they be electromechanical or static relays, are made up of a combination of discrete devices and circuits, each with specific functions, such as signal level detectors, polarity detectors, timers, comparison circuits, logic circuits, output devices, DC power supply for the relays. Generally speaking, standard circuits have been developed for these functions and are widely used in static relays. As an example, this diagram shows the transistor circuit for a level detector. The input signal is rectified to a DC voltage, and when this level exceeds the preset point, the output is switched on, and a relatively large current flows through the operating coil, which initiates action. The equivalent circuit using an IC chip is shown here. You'll recognize the operational amplifier. In both of these arrangements, as the input signal level decreases, the point is reached when the relay resets and is again ready for operation. This reset point can be varied by adjusting this resistor. Reducing the resistance brings the reset voltage closer to the operating voltage. In fact, the reset voltage can be made quite close to the operating level, a distinct advantage over the electromechanical relay. This diagram shows the transistor circuit for a timer. The delay is provided by a resistance capacitance circuit. Remember, we are using DC, so some period of time is needed to charge the capacitor. The series resistance can be adjusted so as to adjust the charging time, that is, the time delay setting of the timer. When the timer is at rest, the transistor is conducting and acts as a short circuit across the capacitor. When the timer is switched on, the transistor moves to a high impedance and the capacitor begins to charge. The curve for the capacitor voltage against time looks like this. The second terminal here serves as a reference voltage VR1. When the capacitor voltage VC rises to VR1 or some other predetermined level, the required action is triggered. For example, this voltage could be detected by the level detector circuit that we just looked at. To reset the timer, the transistor is switched on again, and this effectively discharges the capacitor within a few milliseconds. Let's take a look at polarity detectors. This diagram shows us the integrated circuit arrangement. The essential feature of this circuit is that the output is in phase with the input, but it's in the form of a square wave. This makes it easy to detect precisely when the sine wave crosses the 0 point. One of the main uses of polarity detectors is to measure the phase difference between two sine waves from two different sources. Phase comparison is used for directional relaying, which is required in many types of protection schemes. In this particular phase comparison circuit, the square wave output from each polarity detector is compared in the so-called coincidence detector. Supposing the two sine waves are slightly out of phase, the respective square waves will look like this. The detector will only provide an output signal when both incoming signals are positive or both are negative. There is no output when they are of a different polarity. The resultant output is a series of DC pulses like this. The time period of each DC pulse depends upon the phase angle between the two inputs. The mean DC voltage of these pulses can be measured by integration, usually by charging a capacitor. It will be maximum when the inputs are in phase, and it will be minimum when the pulses are 180 degrees out of phase. This circuit is most useful for measuring phase angle because it is quite independent of magnitude. But it can only produce a result every 180 degrees, that is, every half cycle, 8.3 milliseconds on a 60 hertz system. Actually, measuring the mean DC voltage is too slow for some protection devices, particularly directional or mole relays, where it's extremely important to detect the condition of 90 degrees phase angle difference. A faster way of achieving this is to measure and compare the mark and interval times. These are equal when the phase angle reaches 90 degrees. The detector output is fed into an integrator where a capacitor is charged by the voltage pulses and discharged during the intervals. At low phase angle differences, the capacitor charge accumulates and rises to a preset tripping level. At higher phase angle differences, the capacitor voltage is repeatedly discharged and will not rise to the trip level. The specific phase angle for tripping is adjustable. Be aware that some similar types of circuits may work the other way around. That is a shorter pulse for lower phase angle. Also, keep a lookout for other types of phase comparators, which are also used in static relays. We also employ amplitude comparison. In one common type of amplitude comparator, the two incoming signals are rectified and connected in opposition. That is, one to trip and one to restrain. The resultant DC signal represents the difference, IA minus IB in this instance. To provide direct comparison, the rectified signals need to be completely filtered. A disadvantage of this is that a filter capacitor introduces a time delay. Improved performance can be obtained by phase splitting before rectification. Here, the input AC signal is split into 6 components, each 60 degrees apart. Each of the 6 components is rectified separately, and the resultant DC is effectively filtered within about 5%. Let's take a look now at the 4 most common types of logic. First, the AND gate. In the electromechanical version, we have 2 sets of contacts in series. Both A and B must be closed in order to provide output. This is the symbol for the solid-state version. Again, both A and B must supply input in order to provide an output at C. This condition can be indicated in tabular form like this. These are known as truth tables. For each of the input conditions, the resultant output is indicated. A variation on this is the NAND gate. This is shown by 2 sets of contacts in series, which actually shunt the input signal to ground and so reduce the output to 0. This is the negative version of the AND logic gate that we just saw. The truth tables are shown here, and this is the solid-state symbol. Note that A and B together provide an output of 0, as indicated by this small 0 symbol. I'm sure you've seen this before on logic diagrams and digital circuits. Now let's look at the OR gate. In the electromechanical version, there are 2 sets of contacts in parallel. Closing either one or the other will provide an output. The solid-state symbol is shown here. In this case, A or B will provide an output equal to 1, the digital symbol for a positive voltage. And here is the negative, that is the NOR gate. You can see from the electromechanical version that when either contact is closed, the output will be 0. Similarly, the solid-state version shows an output of 0 if either A or B or both inputs are present. The actual solid-state circuitry for a NAND gate will look something like this, in this case using complementary metal oxide semiconductors. We have looked at the 4 basic logic circuits. Now, there are, of course, other logic arrangements, often custom designed using digital circuits such as PLA, that is a programmable logic array. Now let's turn our attention to the thyristor switching circuit. In practice, the output circuit of the relay would be a little more complicated, like this. The input signal is fed in through the isolating transformer. The capacitor, located here, is to prevent the thyristor from being triggered by spurious pulses, which may be caused by interference. When the desired signal level is reached, the low-power thyristor is triggered, and this in turn triggers the main thyristor. Sufficient current now flows through the auxiliary tripping relay to energize the trip circuit and open the circuit breaker. As the circuit breaker opens, the breaker auxiliary contact also opens, and this in turn breaks the circuit through the thyristor, which once turned on does not turn off by gate control. If multi-tripping is required, then the thyristor will operate an auxiliary electromechanical relay, which in turn will close contacts in multiple circuits. Now, let's take a look at static relay power supplies. Most transistor circuits work on a specific DC supply voltage between 12 to 30 volts. This can be provided from the station battery or local tripping battery. A dropping resistor lowers the voltage to the relay's terminals to the desired level. As the battery voltage is essentially unregulated, each relay will generally include its own voltage regulator in the form of a Zener diode circuit. This is connected so that it will pass current in the reverse direction as far as the diode is concerned when the voltage exceeds a preset level. The increased current flowing through this resistor provides the necessary voltage drop for correction. This circuit also includes a limiting diode which protects the relay by blocking all current flow if the terminals are connected with the wrong polarity. And a filter is provided to absorb any transients that are contained in the incoming DC supply. In some complex protection schemes, it is preferable to maintain isolation between the DC bus and the relay DC circuit. In this case, a DC AC-DC converter is installed. The incoming DC is converted to a square wave AC by the oscillator, then transformed, rectified, and filtered. Another method of providing power to the relay is by using the input current from its own CT or VT. Here, the input signal is transformed to an appropriate voltage, rectified, and regulated. Once again, a capacitor is installed to absorb transients. A disadvantage of this power supply arrangement is that it increases the burden on the CTs. In some relays, power supply is by a combination, that is, from the station battery and/or the measuring circuit CTs or VTs. Where the power source is AC, it is extremely important to protect the static relay against transient overvoltages or voltage spikes. These spikes may damage semiconductor components and at the very least will cause incorrect operation. Voltage spikes can be caused by normal operations on the power system, such as switching or system faults. Protection for the relay is provided by connecting surge diverters at appropriate locations. Typically, the diverter consists of a capacitance connected across the relay terminals, plus a resistor or inductor in series. This is an example of a surge suppressor for a full wave rectifier. Inside the relay itself, non-linear resistors, such as MOVs, are connected across contacts, and any inductive coils which are in series with the contacts. As you know, the metal oxide varistor offers high resistance at low voltage, but breaks down to low resistance when the voltage rises above a predetermined limit. Input leads to the relay should be shielded or screened and grounded so as to prevent interference. Care must be taken when grounding screens so as to prevent the possibility of ground fault current flowing through the screen and destroying the cable. You will remember that we discussed the problem in earlier tapes. In some circuits, transformers are fitted with a grounded copper screen between the windings. This is to prevent the transfer of interference signals across the transformer. On some systems, special equipment's installed to register and count the number of transient overvoltages that occur. However, this information is more useful to the design engineer than relay personnel, who, as you well know, are obliged to operate with the equipment which is already installed. At this time, then, let's take a break. We'll come back and look at some typical static relays after that. But for now, please switch off the tape and thoroughly go through this material in your workbook. Now that we have examined the basic components and circuits, let's see how these are put together to make up specific relays that have similar functions and characteristics to electromechanical relays. Keep in mind that we are showing just a few examples, as this is, after all, an introduction to static relays. You'll have to spend some time studying the instruction manuals related to the specific relays installed on your own power system. First, let's examine the time over current relay. The block diagram looks like this. The incoming signal from the CT is rectified and passed into the fault detector, and from here into the timing circuit. When this times out, the trip detector will trigger the tripping circuit. Note that the relay must be provided with DC power to operate the tripping circuit, the trip level detector, and the fault detector. Let's look at these components in more detail. This diagram shows us the incoming AC signal and its associated rectifier. The current from the CT is usually too high for the relay, and therefore an auxiliary CT is fitted into the relay. The ratio may be as high as 1,000 to 1, reducing, say, 5 amps to 5 milliamps. Taps are provided for adjusting the relay pickup and current range. An RC spike trap is normally located on the auxiliary transformer secondary. Full wave rectification is provided with a filter capacitor in the output. The DC current circulates through this resistance, which in turn sets up a corresponding voltage. Note the polarity. It is positive at the bottom terminal and negative at the top terminal, while the tapped terminal is somewhere between the two. The fault detector unit is connected to the rectifier unit like this. In normal operation with no fault, the transistor is conducting. However, when a fault occurs, the voltage on the transistor base becomes biased in the negative direction, and this in turn forces the transistor into the non-conducting mode. The timing circuit is connected across the bottom rectifier unit terminals. The output of the transistor and the timing circuit are connected in parallel with this jumper. As long as there is no fault, the timing circuit capacitor is short-circuited by the conducting transistor. Hence, the capacitor will not charge. However, as soon as a fault occurs, the short circuit is removed and the capacitor starts to charge, the time being dependent upon the magnitude of the current. Now, we'll connect the trip circuit to the output of the fault detector and timing circuits. This second transistor here is used as the triggering circuit for the output transistor. The emitter voltage is adjusted by this variable resistor. When the timing capacitor voltage exceeds the emitter voltage by a predetermined amount, this transistor will start conducting, and this in turn will operate the output transistor and thus trip the relay. When the fault is removed, the fault detector immediately goes back to the conducting state and discharges the capacitor, thereby resetting the relay. The actual time delay and inverse time characteristic can be varied by changing the timing circuit. For an instantaneous unit, there would be no timing capacitor. Instead, the current will flow directly to the triggering transistor. Many overcurrent and other relays require directional elements. This is generally achieved by phase comparison. Now, we saw an example of this in the last segment, applying the coincident detector. Another coincident method uses a pulse to represent the peak value of one measured quantity, say the polarizing or reference voltage A, while the second quantity, B, say current, is represented by a square wave. Here is the logic diagram. A 90-degree shift is applied to the A quantity. Once the input phase difference becomes greater than 90 degrees, the pulse and block will not coincide and no tripping will occur. Note that the reference quantity A, in this case, remains fixed. Directional relays also use the rectifier bridge comparator. This compares the amplitude of the two inputs, say voltage and current. The relay receives the signals V plus I minus V minus I. The maximum value is obtained when V and I are exactly in phase. The specific value can be determined for different phase angles, thereby allowing the relay to be set for any desired phase angle. This type of relay is also used in generator differential protection. Let's take a look at this. This diagram shows the CT connections for one phase only. This auxiliary CT vectorially summates the CT currents, while this one vectorially measures the difference. The voltage difference becomes the operating signal, while the voltage sum acts as the restraining signal. These outputs are connected into the three-phase comparator circuit like this. The signals are rectified and the outputs from all three phases are paralleled. The restraining voltage on one side and differential voltage, that is the operating voltage, on the other. The output from this amplitude comparator is fed into this trip circuit, which is essentially the level detector that we examined earlier. At any particular instant, the DC voltage present will be the highest of the three phases on either side of the relay. An internal generator fault will provide a high voltage signal on the differential side and a low restraint on the summation side. The result will be a trip of the relay. Now let's take a look at distance relays, which operate essentially by comparing phasors of voltage and current. In the electromechanical relay, this is quite straightforward because the voltage and current circuits are separated. However, in the solid-state relay, as the circuits are interconnected, we must convert the two values to the same units, either both voltage or both current. For a voltage comparator, the current is passed through a replica impedance, ZR, which is tuned to the same value as the line. The voltage drop across this impedance, IZR, is then fed into the amplitude comparator to be compared with the measured line voltage in the same phase. In other types of relays, equivalent current values are compared. In this case, the VT voltage signal is applied across the replica impedance so as to produce proportional current. In a simple impedance relay, the direct amplitude comparator may be satisfactory, allowing tripping on high current and low voltage. However, for the more sensitive distance relays, it is essential that the phase angle and direction of fault current be accounted for. Hence, some form of phase comparison must be used. We looked at some examples of phase comparators in the previous segment. Certain types require the input quantities to be arranged like this, so that the comparator can measure A plus B minus A minus B. This is achieved by adding the signals V and IZR in one transformer and subtracting them on the other. These signals are then compared, integrated, and fed into a tripping circuit. And here is another arrangement that combines amplitude comparison with phase comparison using rectifiers. The amplitude side provides trip or restraint, while the phase comparator is a permissive, allowing operation only within a specified phase angle. A more precise method of controlling operation of the distance relay is by use of a sequence comparator. You'll remember this circle characteristic for the Mo-type relay. If the measured impedance falls within the circle, the relay will trip. For comparison, voltage values are substituted. The measured line voltage lies along this line. The volt drop to the fault IZ lies along this line at the specific line impedance angle. The vectorial difference between these two, V minus IZ, can be used as an indication of fault location. For example, if the fault is external to the zone, V minus IZ will lie outside the circle. In contrast, an internal fault will lie inside the circle. Note that V minus IZ changes angle as the fault location changes. This changing angle is compared with a fixed polarizing voltage in order to determine whether to restrain or to operate the relay. The polarizing voltage is arranged to lag the line voltage by 90 degrees. You can see that an internal fault is indicated when V minus IZ lags the polarizing voltage. With an external fault, V minus IZ leads the polarizing voltage. How is this done? Well, these two sinusoidal quantities are fed into the sequence comparator, which converts them to square waves and then compares the logic sequence. For simplicity, let's call V minus IZ A and the polarizing voltage B. The square wave has only two values, high and low, represented by 1 and 0, respectively. For an external fault where A leads, the signal sequence will read 1 sub A, 1 sub B, 0 sub A, 1 sub B, 0 sub A, 0 sub B, 1 sub A, 0 sub B, 1 sub A, 1 sub B. The comparator's digital logic circuit examines the sequence of ones and zeros and determines whether the relay must restrain or operate. A precaution is necessary in providing the 90-degree lag to the polarizing voltage. If this were to be achieved by an inductor, the signal would experience time delay. Instead, the phase shift is achieved digitally in the sequence comparator itself. Now remember, we're trying to show a variety of examples here. Your specific protection equipment may have entirely different circuitry. Here is a block diagram of one type of static distance relay. This includes a two-zone Mo relay for each phase, shown here. We also have for each phase an offset Mo relay. This acts as a backup for zone 3 and also as a starting switch for the zone 1 and 2 relays. You will remember the significance and characteristics of these relays from our earlier tapes. Also installed are two impedance units. These are really auxiliary relays that block tripping in the case of severe power swings. This diagram, like all of the others, is included in your workbook, so you'll have more time to study details. This schematic shows the connections for just one of the Mo relays in the block diagram. Other relays and other phases are similarly connected. The auxiliary transformers allow us to adjust the impedance operating characteristics of the relay, which may be circular, offset, conic, or others. Again, we discussed this in earlier tapes. The resistors and reactors in the CT secondaries permit us to duplicate the line impedance and so produce the correct voltage drop and phase angle associated with the fault current. This in turn is compared with the line voltage, which is derived from the same phase through these VTs. The resultant is then passed through the sequence comparator, which determines whether the relay should trip or restrain. The polarizing voltage for the comparator is supplied from the same phase, but this receives a 5 to 10% boost from the alternate phases, suitably corrected for phase angle, of course. Clearly, there are innumerable ways of achieving similar relay functions. Static relays are available for all types of protection function. We have looked at just a few here. Many analog solid-state relays include some digital circuitry, especially for logic. Continuous development has led to relays which are all digital, and we'll be talking about this subject in the next segment. For now, switch off the tape and thoroughly review this material in your workbook. In applying protection schemes, we are always concerned with two vital elements. One is the operating time. Usually, we want the relay to clear as fast as possible, except in the case where a deliberate time delay is required. Secondly, the relay operation may be subject to many constraints. We want the relay to operate, but only in the case that certain conditions are met. Indeed, it is these constraints, such as phase angle, direction, and so on, which bring about the complication in relay design. Both of these conditions can be improved by the use of microprocessor relays. In essence, the incoming voltage and current signals are converted to digital format and then compared with the reference values, algorithms, which are already stored in the computer. If the incoming signals agree with all of the conditions imposed by the microprocessor's algorithms, the relay will provide an output signal to either trip, alarm, or perform some other action. As we all know, the incoming voltage and current signals are analog in nature. The amplitude varies continuously. In the analog to digital converter, the amplitude signal is sampled every 2 or 3 milliseconds. Each sample is then converted into a digital signal, which may be an 8, 12, or even 16-bit binary code. As you know, the combination of on and off pulses, that is, zeros and ones in the binary code, will signify the specific analog value that has just been sampled. The digital signals for input voltage and current are then transferred into a memory to be recalled and processed at specific intervals, say every half cycle or full cycle or 1 second, in order to produce A, instantaneous values of voltage and current, B, phase angle displacement, or C, RMS values of voltage and current. Remember, the significant feature of any computer is that it operates extremely fast and can perform all of these calculations in microseconds. So you can see it is not a difficult task for the processing unit to compare these signals with the reference values at predetermined intervals, perhaps every half a cycle. The reference algorithm will, of course, be in digital format to represent one or more mathematical formulae, which in turn simulates all of the operating parameters and constraints of the protected circuit. The algorithm may be set up to represent, say, an overcurrent relay, directional relay, negative sequence relay, differential relay, or any other protection relay. A typical example of microprocessor relaying is this overcurrent relay, which is available as a single-phase unit, or 3-phase, or 2-phase and ground. The block diagram looks like this. Current input from the CTs is transformed and then rectified through a full-wave bridge. The current setting switches select the current range by adjusting the voltage drop across the resistors. The microprocessor includes analog to digital conversion, plus the relay signal processing. For setting the instantaneous overcurrent operation, the high set switches are adjusted. For the time overcurrent function, both the characteristic curve and time can be selected by switches. All of these adjustments are carried out at the front of the relay panel. The output from the relay is low-powered, so it's set up to switch an electromechanical relay, which in turn provides switching power. Let's take a look at another microprocessor relay in more detail, this time a distance relay. Typically, the hardware will be made up of printed circuit boards. These modules will include the power supply unit, the voltage and current input circuits, the A to D converter unit, the main and logic processing unit, the input-output unit. As with other relay units, the power supply is provided from the station battery. In the relay power module, this is broken down to the various voltage levels required by the computer, say plus 5 volts, plus 15 volts, negative 15 volts, plus 24 volts. A memory is included so that even in the case of DC input power interruption, these voltages will remain on for at least 50 milliseconds. Incoming current and voltage signals from the CTs and VTs are further reduced by transformers in the relay. The number of input circuits depends upon the specific relay, but quite often these may include current from each of the 3 phases, neutral current, and voltage for each of the 3 phases. As mentioned before, the A to D converter converts these incoming signals to suitable digital signals. Each of these signals, 7 in our hypothetical example, is sampled, say, 12 times per cycle, and the corresponding digital value is stored in the memory until accessed by the main processing unit. Here in the main processor, these signals are recalled and manipulated according to the relay algorithms. In this particular relay, this will provide impedance measurement, phase angle, Zone 2 and Zone 3 time delay, non-directional backup, etc. The algorithm can be arranged to provide all of the functions that we are accustomed to and more. The main processing unit also includes a logic processor, where the relay signals are compared with incoming relay signals from other protection equipment. For example, pilot protection carrier communication. Such relay signals from other sources are fed into the input-output module. This unit also provides the output for switching and alarm circuits. Output in digital form is also provided for use by other relays or the substation control system, for example, reclosing arrangements. These signals can also be used to operate a digital event recorder or oscillograph. Such signals can also be transferred by modem to a central computer located at a remote location, say the main engineering office or operational center. This facility also offers the ability to reprogram the relay settings from the remote terminal. However, this is more likely to be performed locally. In this case, a small personal computer would be connected into the relay at the appropriate input. Some of the more recently manufactured digital relays are making this programming activity more user-friendly. Instead of having to resort to computer language, the relay technician and engineer can choose from a menu of conventional terms with which they are already familiar. Another advantage of the microprocessor relay is the ability for self-monitoring and self-testing at frequent intervals. Any hardware failures are immediately alarmed or reported over the substation control system. The self-monitoring functions typically include DC auxiliary voltages, A to D conversion, microprocessor RAM, ROM, etc., voltage and current input circuits. Microprocessor relays are quite widely used in industrial plants for protection of large motors. In this particular application, it shows several clear advantages over the electromechanical type. For example, various protective functions are combined in one unit. Also, it is robust and less susceptible to misoperation due to vibration and dusty atmosphere, which often exist in industrial locations. Moreover, it is able to overcome some of the particular problems associated with motor protection and the resultant compromises that have to be made in setting up an electromechanical relay. You'll remember that we discussed this in an earlier tape. Digital relays are usually tested by one of the recently developed test sets, which use microprocessor control. This type of test set applies simulated fault signals to the relay based on the physical parameters of the actual power circuit. Thus, the relay actually responds to perceived fault conditions. The test program for each different type of relay is stored in the computer. This results in a considerable saving of time, particularly with complex relays such as distance relays. We have mentioned several times the substation control system. This is a fairly new concept where the digital signals from data acquisition can be used to automatically control all of the substation activities, including protective relaying, oscillographic recorders, sequence of events recorders, local control panels, local annunciators, SCADA, revenue metering. This block diagram shows the principle of the scheme. Data acquisition units are installed at various locations throughout the substation. Each of these receives voltage and current signals from the nearby circuits, such as distribution lines, bus arrangements, transformers, and so on. The voltage and current signals are then converted to digital signals, and these in turn are transferred by multiplexing to the central computer located inside the control house. The central computer can then process all of these signals according to the various functions. At the same time, it will be connected by a modem to the remote central office. You'll recognize this as similar to the SCADA system that we have discussed in other video training programs. But we must stop here. We're getting away from our main theme, which is protection schemes. Remember, this videotape is intended to be only an introduction to solid-state and digital relaying. But I am sure this should be more than enough to whet your appetite for more information. You can find that by thoroughly examining such installations on your own power system. Make use of the manufacturer's instruction manuals and your own company procedures. Please switch off the tape now and thoroughly review this material in your workbook.